Welcome to the session. First, I would like to thank you all for turning up in the last time slot today. I know it's not easy having to go through all those sessions. I'm going to talk about SDDC reference design for NSX data center with NSX data center for vSphere. Today, let me introduce myself quickly. My name is Dumut Timuralp. I'm a systems engineer in the global accounts team within networking security business unit at VMware. In this session, the goal of the session is to focus on the most common applicable design principles of NSX data center for vSphere. Just to give you, heads up as a start, there are many specific solution-based design guides for like VDI, for platform as a service solutions, and etc. And you may see some slight variations in those design guides, comparing it to what we are going to talk about today. But again, the goal of the session is focusing on the most common design principles of NSX data center for vSphere. So the usual disclaimer, things you should be aware of. I'm sure you are already familiar with this. Let me begin by highlighting the networking and security vision of VMware. This year we launched Virtual Cloud Network, which is essentially all about connecting any kind of application or data regardless of wherever they are hosted. It's essentially a cloud networking fabric as a software-defined architecture, connecting any type of end node or application in a fully distributed architecture. The way we are delivering on this vision is a virtual network infrastructure fully implemented in software with the VMware NSX portfolio. So again, just to make sure, we are going to talk about NSX data center for vSphere offering within the VMware NSX portfolio. I'm going to go through the agenda really quickly, but before that, just a quick show of hands. How many of you have either deployed NSX data center for vSphere or planning to deploy NSX data center for vSphere? Well, all right, so about 70% of the audience, all right. Because I have to set the level straight. This is a level 300 session. Just to emphasize it at the beginning, this used to be a two-part session in the previous VMworld events. Now, I'm going to have to deliver almost the same content in 60 minutes. So I had to hide some of the slides in the content. But after the event, we are going to share the whole content with you by unhiding all those slides. I'm going to try to focus on again, I'm going to repeat myself, sorry about that, but I'm going to focus on the most common design approaches. So, I'm going to briefly touch on use cases, components, then I'm going to dive into the architecture and design. We are going to spend a good amount of time in edge cluster design section, which is mostly most of the people spend the most time on. And then the routing design within that edge cluster itself, facing the physical layer, physical underlay. Then talk about a little bit small, medium, large DC design, and I'm going to close it off with security. But in the security section, I'm not going to focus on any technical details. We just want to give some awareness around how the approach should be like, in our view, when you want to start microsegmenting your applications in your data center. So quickly, use cases and components. With NSX, security has been the most popular one when NSX came out around 5 years ago. And then as more and more businesses started getting the benefits of, started getting tangible business outcomes with network virtualization, with network automation, NSX has become the de facto network virtualization platform for vSphere environments. And network virtualization itself also opened up many possibilities, like the way we do disaster recovery in the networking layer. Not disaster recovery for the applications themselves only, the application layer, or not the disaster recovery that we implement for storage itself or the compute layer itself. For the networking layer itself, it really brought many new concepts. And also this notion of multi-cloud networking, or being able to use multiple data centers just as pool of resources, became much more real with network virtualization as the way we have been experiencing it with our customers. So quickly, through the components, by the way, I didn't mention, I prefer taking the questions towards the end. Otherwise, it's gonna be really hard to cover the whole content here. That's why just keep your questions towards the end. I'm gonna try to, answer as much as I can of all those questions. So you have your physical network in the architecture, which is NSX is completely agnostic of. It can be a layer 2, layer 3 physical underlay, aggregation access core, or leaf spine topology. It doesn't affect any kind of design specific decisions that we would have in the NSX data center for vSphere architecture. Then you have NSX Solutions' own data plane. This data plane consists of ESX hosts, and we realize some components on these ESX hosts. So there are two types. One is distributed services. It's all about distributed packet processing when it comes to NSX. Distributed packet processing, providing the networking or security services as much as close to the workload itself. So the way we implement this is, the way we implement the distributed services is in the form of kernel modules, and also we have another component called NSX Edge, or Edge Services Gateway. A little bit of, too many acronyms. But NSX Edge runs in the form of a VM, and it provides the centralized functions, because ultimately this architecture will have to be connected to the physical world. So there should be an exit and entry point to this NSX domain. So NSX Edges introduces that capability in the form of VMs. Then you have the control plane layer. With control plane, you have the NSX controller cluster. The NSX controller cluster's main functionality is to keep an eye on all those network overlays, which workloads are running in those overlays, with which MAC and IP addresses. All those mapping database live in this NSX controller cluster. Then the other control plane component called logical router control VM, which is sometimes a little bit complicated for some roles to pick up. But the easiest summarization for this is the centralized control plane of a distributed router. Essentially, logical router control VMs populates the routing table, keeps an eye on the routing changes in the environment. Then the logical router control VMs themselves are responsible for pushing out that forwarding state through the NSX controllers all the way down to every other ESX host. We are going to zoom into that in the upcoming slides anyways. Then you have the management plane. Management plane is all about NSX Manager, which is again a VM. And you can apply any kind of resiliency or availability function that you would provide for any type of workload. The way you do it, the same principle applies for all these components. Since they're all VMs, you can apply vSphere HA or DRS or any kind of availability and continuity function that you would realize in your vSphere layer. Now, we have another component as well in the management plane, which is vCenter. Sometimes this gets confusing as well. The reason vCenter is also in the management plane of NSX architecture is simply because vCenter is managing the virtual distributed switch in your environment. So the way we realize, the way we provision VXLANs network overlays is in the form of a distributed port group on that VDS. So vCenter, NSX manager instructs vCenter to provision those port groups on the VDS. And most of our customers spend much of the time with all these layers, but sometimes, in some form, it's a wake-up call for the organization in terms of how can I get the most benefit of a network virtualized networking environment with network automation. Because there are so many tools which would automate NSX Manager itself through API calls, but also if you have your own custom in-house platform or VRA or OpenStack, that's when you get the full benefit of network automation in the form of network virtualization. When you dive into more critical components in this picture, the most important thing here is, this is just to provide you a guidance of which kind of things that you should keep an eye on. Like, usually the most focused pieces CPU or memory requirements of these components, but in terms of data plane, in terms of control plane, there are so many differences. The easiest one as an example that I can give you is DLR control VM or the logical router control VMs represents the control plane of a distributed router. So all we would care about is availability or convergence. But when it comes to NSX Edge VM, NSX Edge VM is both a control plane and a data plane component. So it sits in the data path. So it's not only about availability and convergence when it comes to NSX Edge. It's also about scalability, scaling your bandwidth. It's also about services that you would implement on that NSX Edge. And I know I mentioned this already, but we have an NSX design guide published on VMware Community's page, which is more than 150 pages long, which covers almost 90% of whatever you would want to implement with NSX. So, like I said, this session was a two-part session in the previous VMworlds. So, design guide has much more detailed information on itself. On the contrary, on the other hand, this deck doesn't cover the additional features that we have introduced with 6.4, like multicast support, like context-aware firewalling, and other features. We are still investing in NSX Data Center for vSphere. Also on the usability front, we have introduced so many new features throughout 2018. Let me jump on to architecture and design quickly. The most important pieces, the best practice that we recommend is using a dedicated management cluster. So as you can see on this slide, the NSX edges and DLR control VMs are hosted in the edge cluster domain. And you don't see any NSX Manager or vCenters in this picture. The reason is NSX Manager and vCenter is running in a separate management cluster, but not just physically separate, but also that management cluster is being managed by a different vCenter, which you see as vCenter VM management right in the center of this slide. So the reason you would want to do is the quick ones that I can tell you about is avoiding any kind of circular dependencies in upgrade scenarios, like upgrading the ESX cluster itself wouldn't affect the vCenter VM's continuity. And also, if you have multiple vCenters in your architecture, then it provides some form of a mobility for the management components in that management cluster, because you can extend that cluster in the data center between different racks and etc. Now, the most important piece on this slide is the controller placement. NSX controllers should be placed on an ESX cluster which is managed by the vCenter which NSX manager is pointing to. I know it was a long sentence, but that is the main architectural requirement. So as you can see, NSX manager VM domain A is pointing out to vCenter for domain A. So controllers has to be running in a cluster which is managed by vCenter domain A. So that is the main thing that I would like to highlight on this slide. Now, if you're interested in multi-site networking security, there is a dedicated session for that in VMworld, which you can attend. ESX VM kernel networking. We need 4 VLANs in any kind of physical underlay. As I mentioned, we are agnostic. NSX is agnostic to the physical underlay. The reason we would want to dedicate different VLANs for different types of traffic could be quality of service, could be monitoring, and etc. Usually, most of the network engineers by themselves, they prefer a dedicated VLAN for the overlay encapsulation, simply because to get better visibility into that, in that data center about the overlay encapsulation traffic, how much is it, and etc., etc. Now, the tunneling functionality, the overlay functionality, VXLAN functionality on an ESX host is implemented in the form of a VM kernel interface, which you see as VMK3 on this slide. That is where we start processing the traffic or start putting the traffic into an overlay tunnel. Now, the most important piece in this picture is the third bullet, which says VXLAN VLAN ID must be consistent. This is usually overlooked, but the reason for this is you are supposed to prepare a cluster for NSX. So NSX data center for vSphere is installed per cluster. So when you choose a cluster in the GUI and when you click on configure VXLAN, you would see a new configuration screen coming up. And in that configuration screen, it requires you to specify a VDS. It requires you to specify a VLAN ID. So how would this affect the whole architecture? When you stripe that, or when you span that compute cluster across different racks, that means the same VLAN ID has to be consumed for this functionality. And there is no side effects of this. Either in a layer 2 or layer 3 topology, you can use the same VLAN ID in different racks, simply because that VLAN will be terminated on the top of rack switch in that rack. So you don't have to extend that VLAN from one rack to the other. That VLAN will be, the rack itself will be the boundary of that VLAN. But the VLAN ID itself, simply because how we install NSX per cluster, the VLAN ID itself has to be the same over different racks. Is everyone fine with that concept? Did I, do a good job explaining it? I'm seeing some, heads nodding, some heads totally miserable. Let me give it another round really quickly in less than 15 seconds. You click on the cluster, you configure the, VXLAN parameters, so there is a single VLAN ID that you can specify in that screen, in that configuration screen. So that means for that cluster, you are going to implement VXLAN on a single VDS, and for that VXLAN functionality, there will be a single VLAN ID being consumed. That's why if you span the compute cluster over different racks, you need to keep an eye on using the same VLAN ID on every other top of rack, regardless of your underlay, whether if it's layer 2 or layer 3. That is something to keep an eye on. And since actually, as every other encapsulation protocol, you need a higher MTU size with VXLAN, which we recommend as 1600, but we also strongly recommend to future-proof your physical network by moving forward with jumbo frames or by moving forward with MTU 9K. That would help a lot in, IP-based storage implementations, or that would help a lot in any kind of future implementations that you would want to do in your data center. Now, there is a VMware KB that we are referring to about that to give you guidance on how to configure MTU 9K on VDS. Now, VDS uplink design. This is the second most important thing in the design phase. The reason is, like we mentioned, NSX creates a new VM kernel interface for VXLAN functionality, and that VM kernel interface is supposed to be connected to a port group on the VDS. So, on this slide, we are talking about the teaming mode of that port group, which the VMK3 is connected to. So, for that port group's teaming mode, we recommend route based on originating port, which is actually the default setting in the teaming modes. The reason we are discouraging LACP is actually there are multiple reasons. The ones I can quickly highlight to you is, as soon as you start using LACP on the VDS, you don't get to have the flexibility of using different teaming modes for different port groups on the same VDS. The reason you would want to use different teaming modes on a VDS is for dedicating an uplink for some specific traffic. Like, I would prefer my management and storage traffic go through this PNIC, this physical NIC on my host, and data plane traffic to go through this other physical NIC on my host. These kind of things won't be possible with LACP. LACP will just process the traffic based on hashes, so it's kind of, not that easy to identify through which path your traffic is going through, especially in troubleshooting sessions. The other thing is, which I'm going to zoom in quickly, once you want to run any kind of routing protocol over an LACP connection, then not every other physical switch vendor or not every other physical switch model supports that. So it brings more complexity into the picture. And this is a software-defined networking architecture. So by definition, we would prefer to completely decouple all the intelligence from the physical underlay. As soon as you do LACP, it means multiple teams will have to get involved in that troubleshooting session. The reason is LACP is a dynamic protocol. There are some protocol data unit exchanges between the physical switch and the VDS. These are the ones that I can quickly highlight, as I said. But this doesn't mean that we never use LACP in the environments. If it's a brownfield environment, if LACP is already being consumed, then of course that's the way to go. With VXLAN design principles, when it comes to replication modes, since we are emulating a multi-access Ethernet broadcast domain, ESXs have to replicate the traffic. Usually we recommend unicast, but if your environment, if the growth rate of your environment is really high, and if you kept on using the same subnet for that VM kernel 3 interface, then we recommend using hybrid mode, which offloads the replication into the physical underlay. This is one of the 3 most important slides in this deck, so I would kindly request your full attention with this slide. The reason is, transport zone concept is all about the boundary of a VXLAN. But there is always a misconception of transport zone being a security measure. That's definitely wrong. The reason is, you can ping between 2 different VMs in the same VXLAN into different clusters, even when one of those clusters are not part of the same transport zone. There are technical details into this which I don't want to cover right now for sake of time, but the usual principle with transport zone is in multi-tenant environments, the network automation tool or the hosting provider usually want to dedicate a VDS per tenant. So in those environments, we would recommend to align your transport zone with the VDS. Here, as you can see, we have two VDSs though. The reason is edge for north-south connectivity functionality, which our NSX edge is running for, are connected to a different edge VDS, a different VDS called edge VDS. The reason for this is network engineers usually need to spin up some additional functions on that VDS, which your north-south connectivity is happening. And also on top of that, again, back to the LACP teaming modes, you would want to leverage different teaming modes only for NSX edges, only for the ESX hosts, which those NSX edges are running on. That's why it's a very good practice to keep that VDS as a separate component in this architecture. So quickly diving into the edge cluster design, the reason we spend most of the time in this specific section is, or in this specific design consideration is, there are many factors. Like, do I need to use ECMP edge design? Is active standby HA-based ECMP, active standby HA-based NSX edge design sufficient for me? What type of workloads am I going to be running in my data center? Will those be resource and bandwidth intensive applications? Will that affect my scale in the months and quarters coming forward? These kind of design decisions affect many other different things in the design process. So with NSX edge sizing, the two things I would like to highlight on this slide is, if you want line rate performance on an NSX edge, we definitely recommend quad large size. If you are going to use higher layer load balancing, like layer 7 load balancing with a high performance requirement, then we definitely recommend X large size for that functionality. Highlighting logical router control VM component again, this is a control plane component. So if your logical router control VM pair goes down, if the NSX controller cluster goes down, the data path remains unaffected. But unaffected in the context of the data path, the routing tables on the ESX hosts will preserve the end state before that failure, before that logical router control VM failure. If you had 10 routes, some of them BGP, some of them OSPF or whatever, those routes will still stay in the ESX host DLR kernel module routing table. So it doesn't affect the data path, DLR control VM failure or NSX controller cluster failure. The most confusing thing when you start learning about NSX is, and I'm sure most of the people here has gone through that process, the southbound links of the DLR control, the DLR itself, called logical interfaces, LIFs, and those, I mean, let's take LIF1 as an example. LIF1 has an IP and a MAC bound to it, tied to it. So that IP and that MAC address will stay the same across your ESX hosts. The same IP and same MAC. I'm talking about the interface of the DLR itself. The reason this doesn't cause any issues in the physical underlay is because in a typical physical underlay with spanning tree enabled, the same MAC address cannot be shown on or cannot be seen on different ports. This MAC address always stays in the overlay network. This MAC address is only seen by the VMs themselves. This MAC address is always in the inner header of the VXLAN encapsulation. That's why essentially physical underlay never sees this MAC address. So that's why it runs flawlessly with the great benefit of network virtualization. The good thing is all the things I have mentioned here are just implemented in software. So You can pick any kind of topology. Like if your east-west traffic is really, bandwidth intensive, you can deploy distributed logical router for your production workloads. If some application teams need an isolated environment, you can put an NSX edge on the right-hand side. It's shown inline LB with netting, with private networks. You can implement that topology, and you can scale out this topology per tenant, per application, in whichever way you want. Of course, based on the design requirements, design outcome of the architecture. If it's highly, highly not resource, but bandwidth intensive environment, of course, we would recommend using scale out ECMP edges northbound as it's shown here. And the second thing is, with automation, this can be quickly replicated, like with the help of vRealize automation or with the help of OpenStack. It is a scalable platform, and the things that you should be focusing on, at least the columns that you should be focusing on, is again the workload types, whether if those workloads will be bandwidth intensive, that will have an effect on your cluster design. And also, if there is too much automation that will be implemented in this environment, then again that will push you all the way to a higher bandwidth state for north-south connectivity, and also a separate cluster-based design, which I'm going to cover in the upcoming slides. After all these different things, you get to have a, rough understanding of how many edges, how many DLR control VMs, how many service edges we call them, like the edges which you have load balancing enabled on or netting enabled on. It comes to the placement of these components in the edge cluster. As shown here, minimum 4 hosts is recommended for the edge cluster. This doesn't mean that you can run all these things in a single ESX host. Of course you can do that. But the best practice is to cover as much as failure scenarios as we can. The best practice is minimum 4 hosts. And the reason for that is the compound failure scenario of ECMP edge with the DLR control VM. The basic reason for that is you would have DLR facing northbound to different ECMP edges, which means the same DLR would have equal cost path through different edges. Let's consider the failure scenario of one ECMP edge failed at the same time with the logical router control VM. So for a certain amount of time, until the standby logical control VM takes over, the forwarding state of all the ESX hosts will still see that failed edge as an active edge, although it is failed. So if you have a 4 ECMP edge based topology, 25% of your traffic will be black holed because of that failed edge. So to cover this failure scenario, we require you to put the DLR control VMs in separate hosts. That's why you see 2 ECMP edges in 2 ESX hosts in this cluster. And the way we make sure these components run in this way is VM rules or DRS rules. For ECMP edges, DRS rules are not configured automatically. And also for NSX controllers, DRS rules are not configured automatically, but for DLR control VM, since it's an HA couple, high availability couple, the DRS rules are configured automatically. Now, there is one thing wrong here, which was an editing error. The host uplink for this edge cluster is explicit failover. So using one of the physical links and the other physical link for other edges. I'm going to deep dive into that in the upcoming slides anyways. Then here comes the academic discussion of oversubscription. I'm a network engineer by heart. My whole background is network and security engineering. you will always have some kind of oversubscription in your physical network anyways, but still, even within that context, let's say you have on the left-hand side, you have 2 ESX hosts, 2 by 10 gig ports per ESX host. If you put 2 NSX edges per ESX host, that would be a one-to-one model, which means no oversubscription at all. Because each NSX edge, based on a 10 gig physical NIC design, can go all the way to line rate. Per NSX edge, we can provide 10 gigabit per second of throughput. On the right-hand side, as you can see, if you put 4 edges per ESX host, then that means injecting 40 gig per second traffic to a 20 gig per ESX host connectivity. Now, quickly covering the topologies, you can use an edge HA pair, and you can provide stateful services on those edges. And in this topology, the most important thing is the routing timers. The reason the routing timers are set to higher values is we support graceful restart. So whenever one of the edges fail, the standby edge takes over, and that standby edge sends a graceful restart protocol packet towards the physical router in the underlay, northbound, saying that I am having a process switchover, CPU switchover, so please hold on to your routing protocol neighborship, please hold on to keep your routing state as intact. So that's why for graceful restart process, for that connectivity to kick in, we keep the routing timers with higher values. With ECMP, of course, south to north and north to south traffic won't be the same all the time, because the hashing function can send south node traffic for a specific workload type through ECMP edge 1, and the return traffic could be coming back through ECMP edge 8. So simply because of that asymmetric data path, of course, stateful services won't be supported in this kind of an architecture. And on the contrary, we recommend very aggressive timers in this topology. The reason is, if one of the edges fail, simply for the DLR to update its routing table in a really fast nature, like in a couple of seconds. That's why you see the aggressive routing timers as 1, 2, 3, as set to 1, 2, 3. So in this topology, when one of those edges fail, you would only see loss of traffic all the way down to 12% or so. The traffic that will go through edge 1 throughout those 3 seconds will fail. This is a pretty good failover or failure time. The reason is with TCP it's easy to recover. Of course, with audio or video traffic, 3 seconds or multiple seconds won't be enough, but that type of traffic you would see in a wide area network or campus network. So to wrap up quickly with the topology, you start out like this with the distributed logical router for your east-west traffic. For optimizing your east-west traffic in your data center, you would implement distributed logical router. Then you pair it with NSX Edge, northbound, which is a VM. And the way this works is DLR control VMs form those neighborships, those routing protocol neighborships, either through OSPF or BGP. Then as soon as DLR control VM populates its routing table, it pushes out that routing table all the way down to every other ESX host in your environment. So when you want to scale out this architecture, why would you want to do that? Based on your workload requirements, your growth rate with the workloads may be really high. So you may want to increase your bandwidth. You simply scale out the edge layer. And with that, if you use 40 gig physical NICs on your ESX host, then that means your north-south traffic can scale out all the way up to 240 gigs. Because the reason is with a 40 gig physical NIC, you can go all the way up to 30 gig bandwidth, 30 gig processing bandwidth per NSX edge. There are some slides on this which are published on VMware webpage and also in previous VMworlds in terms of what was the principle with those, testings, like the packet size, the, NIC vendor or CPU requirements, etc., etc. But this is per tenant or per application, 240 gig of bandwidth connectivity with the physical underlay. So, of course, if you spin up more workloads, more topologies, then you can easily scale out further than 240 gigs. And in terms of tenancy, in terms of isolation, of course, different types of topologies would be segregated in the physical underlay in the form of the VRF functionality that the physical underlay can easily provide. So this is how you would segregate those functions or those topologies from each other by utilizing VRF in the physical underlay. Quickly moving forward with the cluster design. With compute cluster, I'm going to repeat myself again. It's all about the workload characteristics, because that gives you an idea, and that is the most decisive thing on what your CPU requirements will be like. If you would put like, I don't know, 50, 60 VMs per host in terms of VM to host consolidation, you would want to use more physical NICs on the ESX host. So your compute cluster should be architected in a way which you can replicate the same hardware configuration easily to different racks, or write the opposite based on the SLA requirements per application. Maybe you have to architect, or you have to come up with different types of hardware sizes, different types of compute server characteristics per cluster. We have this notion of separating every other cluster from each other when it comes to that management, control, and data planes. As you can see here, there is a management cluster concept in which you would put your NSX controllers, NSX manager, and vCenter in. And then there is the edge cluster, and then there is the compute clusters. This is the ideal topology, ideal design. The reason you would want to do this is operational characteristics may push you to this model. The reason is upgrading a compute cluster, the way you would ask for a maintenance window in your organization may be totally different than asking for an upgrade on the edge cluster. Operational reasons, control boundaries may be the other reasons for moving forward with this model. And of course, scalability-wise, if you want to hit the highest scalable environment in your organization, then you definitely, eventually, ultimately, have to segregate these functions into different clusters for availability reasons, for resilience reasons, for bandwidth reasons. But this doesn't mean that you cannot start with a small design or a single cluster design. Most of the POCs, most of the proof of concepts actually start out with this, with the minimum level of requirements. And then what you do is scale the environment out to different clusters. As shown here, management edge cluster is collapsed here. The reason is management components do not require, high CPU cycles. There may be some spikes with vCenter or NSX manager. For instance, for NSX, pushing out 20,000 rules with object to IP conversion requirements through the NSX manager may cause a CPU spike on the NSX manager, but not every other minute, not every other cycle. So that's why the management components being collapsed into a single cluster with the NSX edges is the best way, to start with in a medium DC design. And also, when you scale out, as we mentioned, in a large DC design, large or ultra large, however you put it, You definitely would want to consume different clusters for different functions so that you can easily scale out the edge cluster itself based on the workload characteristics. I've seen many cases in which workload requirements vary a lot in this type of environment, large design environment, that the first decision of NSX edges, number of NSX edges, etc., quickly change over a couple of months. The good thing is you can change the NSX edge size on the fly. You can spin up additional NSX edges on the fly, especially when you leverage network automation. That is pretty cool. But also with cross vCenter and SRM scenarios, those implementation models also push you to an dedicated management cluster anyways. So with routing design really quickly, the first message is we don't recommend using LACP. On top of all the reasons that I mentioned already, like having to use LACP for every other port group on that VDS, not being able to segregate your traffic, etc., etc. But also the notion of software-defined networking is decoupling the intelligence from the physical underlay. As soon as you implement protocols like LACP between the physical underlay and the ESX host and the VDS, at least what we experience in the field is you introduce another layer of sophistication or another layer of mixture into the equation, in which, like I mentioned, multiple teams end up having to troubleshoot, etc., etc. And on top of all that, not every other physical switch vendor supports routing over LACP, or not every other model of switch supports routing over LACP. You suddenly realize that your line card you have, or the specific switch model doesn't support routing over LACP. And we simply, as VMware, cannot QA, test, and validate every other possible scenario with every other vendor in this kind of a topology. So that's why we don't recommend using LACP. What we recommend is using a very deterministic way of connecting one uplink of NSX edge through a single physical uplink of the ESX host. Like it is shown here, the left-hand side NSX edge uplink is paired with the left-hand side ESX host's left-hand side physical uplink. So you use dedicated uplinks for dedicated peerings, something like this. And believe me, there was no easier way of showing this on a slide. This is the best I could come up with. But what we mean is, on an NSX edge, you provision two uplinks, and those uplinks are using different VLAN IDs, but you map each VLAN to a physical uplink on the ESX host through teaming. This provides you a very deterministic way of troubleshooting when something goes wrong. Usually, if the organization moves forward with a single VLAN ID for peering with the physical underlay, then that means if someone accidentally deletes that VLAN, your whole peering goes down with the physical underlay. So these kind of details provide you this guidance. And this is what we recommend, as I mentioned. But with Cisco UCS blade chassis architecture, you still have to move forward with, not move forward, but most probably you already started using VPC. So what we recommend is using dedicated routing links other than those VPC links between the UCS chassis and the physical underlay. With BGP connectivity, the reason we highlight BGP here is we believe that BGP provides you the best control over the environment. It's a path vector protocol with the physical underlay between the physical underlay and the NSX edges. And also, it provides you the most flexible topologies, especially in multi-tenant environments, since we provide private AS numbers for each tenant, those tenants would be automatically isolated from each other. So we recommend using eBGP northbound between NSX edge and physical routers, and also iBGP between the NSX edges and the DLR itself. This is a very technical slide, but just to give you an idea, this is routing in essence. NSX doesn't change any principle of routing when peering with the physical underlay. It's the routing, the same principle that we all know. So there are certain guidelines. The thing that I should highlight is we don't support BGP next hop self. So you need to, in this slide, you need to redistribute that green and blue network with between the physical underlay and the NSX edges to the network, to the DLR itself. The reason is if you don't do that, DLR would see a next hop of the physical router's IP in its BGP routing table, but it won't be able to successfully perform recursive routing for that traffic. That's why that's a slight detail in that context. About NSX security design, I'm quickly gonna go through this. You have your workloads. You start with, the whole essence of microsegmentation is, it begins with DFW, with distributed firewalling. And with distributed firewalling, you turn on logs, you start, identifying your applications. You start consuming service composer. You classify your workloads into security groups. Then you start architecting your security policy. Then this goes on and on when you put additional components into the equation, like third-party service firewalls or third-party guestless agents on the VMs. Now, when you look at a generic security approach, there is, of course, risk assessment. It always begins with risk assessment, risk assess your applications. Then you always, in some context, put your workloads into different zones. That reality doesn't change with any kind of implementation. Then you identify your access patterns, which means application dependencies in your environment. That pushes you, moves you forward with the grouping or classifying your workloads into different groups. Then again, the same architecture of policy modeling, and this goes on and on. So with any VMware networking and security enabled picture, what we do is you insert the distributed firewall into the equation, which is pretty seamless, pretty easy, because distributed firewall is implemented between the VM and the virtual port of the VDS. We don't require any kind of port group changes. We don't require overlay networking right up front. You can use microsegmentation without network overlays to start with, to begin with. So you turn on your default rule. It could be deny all if you want to stay involved as a security engineer so that no one can connect anything without your knowledge to the DMZ, let's say. So their traffic would be denied. Then you would get notified by logging. Then, of course, you have to architect your shared services, which consumes a good amount of time in the design phase or in the implementation phase. Then, according to those log-based findings, you again start classifying your workloads into zones or into different inventory types, and you start using east-west firewall rules. And this process goes on and on. The thing that I'd like to highlight here is this is something that you would never find anywhere else. The original content provider for this session was Nimish Desai, one of our actually our director of solution architect team. He put this together. This just provides you a generic guideline on which use case, actually which tool to start consuming with which use case. We have various tools like VRNI, vRealize Network Insight, like ARM, Application Rule Managers, all acronyms. that you need to keep an eye on. That's why I put the smallest piece on that right-hand side is my piece. That's why I put those, acronyms in a, highlighted fashion. So the way you use these tools would depend on the use case, obviously. With that, this slide is just to provide you the maturity curve that NSX achieved already. We are either, in the evaluation phase or already, validation phase with these certifications. We have recently, not recently, but in the beginning of this year, we got the FIPS Common Criteria certifications as well. And when I said VMware NSX portfolio, if you are not aware of this yet, I meant actually this content. The reason is VMware NSX is a whole product portfolio now. So we have NSX Data Center, which we talked about, NSX Data Center for vSphere in this deck, in this content. We have NSX Cloud, NSX SD-WAN, NSX Hybrid Connect, and also App Defense. And in the management layer, automation layer, we have Network Insight and also vRealize Automation to guide you through all the functionality that network security virtualization provides. And with that, the last thing that I'd like to mention is NSX is a platform. It's not a point product. We are trying to extend this platform to any kind of functions or any kind of additional services that we can provide. As you can see, this slide is pretty busy in terms of logos. So you would find many specific design guides when it comes to the joint solutions that we provide with these vendors. With that, there is many resources on the internet about NSX. I highly recommend Hands-On Labs. We have everything that I mentioned in this deck in the HOL Labs. That is the best way to learn things, at least from my point of view. I'd like to break things as much as possible to see how the solution reacts. So with that, now I can open up to questions. I'm pretty amazed with myself. I usually run over. So just raise your hand if you have a question, and our fellows in the room, they will bring you a microphone. So, yeah, the gentleman in the first row over here.
In the slide 25, medium scale data center design, you have mentioned in the medium scale data center, edge cluster would be merged with management, but not with the compute cluster. Yeah. But as per my understanding, if customers do not want internet connectivity with the management, why? Yeah.
The reason for that is, for the medium design, you still don't use a out-of-band management cluster with a separate vCenter. In the medium design, you use the same vCenter for all the clusters, yet you would still have a separate management cluster for your management components. But there is a single vCenter in that design. So for medium DC design, that concept of a dedicated out-of-band management cluster with its own vCenter doesn't apply. That's why.
But if we merge edge cluster with the compute cluster, because the compute cluster VM, customer VM require the internet connectivity, would be, I think, good.
The reason is it will take more time. It will take more details to design that kind of layer into the mix. But let's take it offline. Let's talk later on the session, because it will take a little bit of time to explain. And I'm seeing 1 minute. Let's take one more question, then yeah.
At the beginning, you talk about the jumbo frame configuration on the 6 side, but we see with some tests that it's not possible to configure a full jumbo frame configuration with 9,000 MTU with NSX, because it won't work because of the VXLAN. And
did I get the question right? I mean, it's not possible to use 9K MTU with NSX. Is that what you're saying in your test?
For example, from a customer VM to...
We support 9K MTU with NSX edges on the VM level and also on the VDS level. Let's take that offline as well, because it works. There are environments using NSX with 9K MTU size for sure.
Okay, thank you.
All right, guys. Thanks for your patience and dedication until this time. Appreciate it. And don't forget to fill out surveys, please, to rate us. And the exit is this way, just so you know, before I forget to mention that.